Yes.
There's been huge news around AI data centers globally. Um, Elon Musk with xAI is building a 1 million GPU data center, which he says he'll complete in 6 to 9 months. And that will have 1 gigawatt of power or more. And he's already completed a data center in Memphis with over about 200,000 GPUs, which have been used to train Grok 3 and Grok 3.5, and Grok 3.5 releasing this week. And in a post, he talked about where he was thinking about how to get to a terawatt of power as soon as possible. That would be doubling the power generation of the United States, which would be a huge monster challenge. And beyond just Elon Musk, there's deals being announced with Saudi Arabia. There's the Stargate project with OpenAI and Oracle down in Texas. There's Kevin O'Leary of the Shark Tank setting up about 7 gigawatts of capacity, 70 billion dollars just for the energy in Wonderland, just in northern Alberta. So there's many deals, geopolitics, huge amounts of energy, probably 10 gigawatts completed this year and 50 gigawatts in the pipeline and rising very, very fast. In the mix is Copenhagen Atomics and the nuclear option, the nuclear energy option. Microsoft paying to restart a mothballed 3 Mile Island a reactor that was shut down a few years ago and now being brought back. Not the one related to the 70s, but a new restarting a reactor. So nuclear is definitely back on the table in order to meet these huge energy demands. With me is Thomas of Copenhagen Atomics, the CEO. Thomas, introduce yourself and give your intro to Copenhagen Atomics.
Yeah, thank you very much. Yeah, so I'm the CEO of Copenhagen Atomics, and we are one of the companies developing new nuclear reactors. We have our type of reactor are maybe specifically interested for this type of application because it's made for a very large scale out. We plan to build an assembly line production where we make more than one reactor every day. We plan to have our first test reactor, demo reactor online in 2027, so that's not too far away, and have the first commercial reactors ready by the early 2030s. I would like to start up by talking about sort of our listeners get a little bit of an idea of the global scale in this. Today, the total amount of electricity in the whole world is roughly 3.5 terawatt. And if you combine Europe and the US, it's roughly 1 terawatt. And that is what Elon Musk has suggested, that he would like to get 1 terawatt for compute. He didn't put any deadline on that, but I assume that before we can have the chip factories ready to make that many chips, it'll probably be 8 to 10 years. It's a little bit, you know this better than I do, but we've already in Copenhagen Atomics, we've already looked at how is the electricity market internationally or globally going to scale out in the next couple of decades, and we looked all the way into 2050. And we looked at different scenarios. Is it likely to double, or is it likely to triple, or is it likely to quadruple? We think that it will more than double. And our best estimate is that it will triple. The total global electricity will triple before 2050. And of course, data centers is a big part of it. But we also need to run all these EVs. They use a lot of energy. We need power to X. That means we will have more and more of the chemical products we make, and also synthetic fuels, airplane fuels, and all kinds of other fuels made with electricity. There's also some of the refineries, oil refineries that use huge amount of energy that would like to convert. And for example, for all the food, all the 8 billion people consume, that fuel is predominant, or that food is predominantly made from ammonia today. And that ammonia comes from natural gas, but many countries talk about changing over and using nuclear and making green ammonia, basically made from hydrogen and nuclear electricity. So a lot of things are happening at the same time, and that's why we as a company predict that we will triple the global amount of electricity by 2050. So that would mean 10 terawatts of electricity by 2050. So viewed in that light, it's not unrealistic that Elon Musk or Tesla or whoever it is, xAI could use 1 terawatt. And he didn't specify that in the tweet. I'm not sure all of that was just for data centers. It might also be for the robots or for the robo taxis or whatever. That's a little bit unclear. But of course, all of those things use huge amount of energy. He also builds all the Teslas out of aluminum, and aluminum requires huge amount of electricity as well. So he's definitely using a lot of energy, or his businesses. And I find it very exciting to talk about how we humans can generate all that energy. And of course, our solution from Copenhagen Atomics might be one of the solutions to this, because we can install between 15 and 50 gigawatts of electric capacity per year in the early, sort of in the 2030s. And then when we get into the 2040s, hopefully even more. But it's a little bit hard to predict that far into the future.
Right. In terms of some of the predictions, just some other support beyond what Tesla and Elon Musk have is TSMC, Taiwan Semiconductor, who makes the vast majority of the advanced chips. If you see this top slide, accelerating AI applications drive silicon growth. On the bottom part of this chart from Taiwan Semiconductor that they gave out last month, we can see that AI data center, AI chips, what they call AI accelerators, which is the GPUs, 5 million units, that 5MU is 5 million units per year, which is the volume production of the B200s, H100s that are still being made, and B300s this year. And then by 2030, in their forecast, they talk about increasing that by 10 times to 50 million units. 50 million units at 2 kilowatts, 2,000 watts per chip, which is what the B200s are, which are up 50% or more from what the H100 were, would be 100 gigawatts each year that Thomas Jam makes them, and then xAI, OpenAI, Amazon, and the other companies buy them, install them, have to power them up. So in order to power them up, they'll need 100 gigawatts each year. And that's just in 2030. The growth, as we've already described, goes to that multiples of world electricity. The line above AI PCs, 100 million per year now, those would be using slightly lower power GPUs, but still more power than the CPUs in laptops now. And that would nearly triple to 280 million units. So the growth of power is being planned out at detail by the trillion-dollar companies, not just Elon alone, but Meta, Taiwan Semiconductor, Samsung, all these companies are planning, putting, this slide just shows that there's doing stuff on the fab side, on the semiconductor side to support it. So the entire world industry is moving in this direction of greater power. So there's a lot of solidity behind what's happening. For Copenhagen Atomics, you're doing the molten-salt reactor, which
Sure.
has been already proven in the 1960s by the US National Lab. And then China has completed a 2 megawatt thermal version of the molten salt reactor. So unlike, for people who don't know that nuclear fusion and nuclear fission are different, and the nuclear fission reactors using uranium and other metals like uranium have been providing about 10 to 15% of global electricity over the last few decades. So they are completely proven, nothing experimental about them. And even your type of reactor has been built in the past and recently. And there is no technical scientific uncertainty that they can be built, because multiple units have been built and operated for many years. Do you want to discuss the molten salt aspect of what you're doing?
Yes, I would like to talk on that, touch on that briefly. So, when we look at different types of nuclear reactors, we want to understand how quickly can they be built, and what are the bottlenecks if we were to build large amounts, sort of several hundred gigawatts of that type of reactor. And there are many different reactor designs out there, more than 50, or maybe even more than 100 different reactor designs. Some of them are microreactors meant for the Navy or military use, or even to put on the moon or something. and other reactors are very large, sort of classical nuclear reactors called light water reactors. Yes, this is an image of our type of nuclear power plant. In this specific building here, it looks a little bit like a distribution center where the roof is cut away, and it has inside it has 30 reactor cocoons, and each one of those reactor units produces 100 megawatt of thermal energy, or which is roughly equivalent to 42 megawatts of electric energy. So a plant like this is a 1 gigawatt electrical output. And the building there we see in the front of the picture is sort of the nuclear part of it. And in the background, we have the steam turbines and the steam generators and other things. But I think we have to sort of make a comparison here. If we expect to make a lot more nuclear energy in the future, we need to make the regulations easier. Because in the past, some of the first nuclear reactors that we humans ever built there was one called Hanford B, which is now a museum in the state of Washington, which you can go and see. That was a 2.5 gigawatt thermal capacity reactor, and it took 11 months for them to build it, and it ran for 25 years without problems. But today, if we look at some of the latest reactors that have been built in Europe or Americas, I mean, there's the 2 reactors in Georgia. They both took more than 10 years. In Europe, we've had reactors that took 15 or 18 years to build and get it licensed. And this is also what the government now in the US is looking at. How can we change the rules so that it becomes easier to license these things? I have another example. In the UK, they are now building a power plant called Hinkley Point C. And the latest estimate is that the total power plant, its 2 units, will cost $62 billion US. And it's clearly way too expensive, and it will also take too long to build. And if you go in and look at that type of power plant and you look at the total amount of concrete, the total amount of steel, all the uranium you need, all the steam turbines, all that hardware costs roughly, at least the way I calculate it, less than $6 billion US. But since the whole thing costs 62, so you can say the idiot index that Elon Musk talks about is higher than 10, meaning that the product price is 10 times higher than the raw materials. And I think this is unacceptable. We have to look at nuclear energy and change the way we build it. We need to build it much, much faster and also get the idiot index much further down. I would love to get it down to 2. That's what we are trying to do with Copenhagen Atomics. So that the price of electricity is only twice the price of the raw materials that are needed for the plant. And this is also why we want to mass manufacture our reactors. But again, I want to give people a little bit of an idea. So all over the world today, there's just about 1 terawatt worth of nuclear energy. And of course, if I say, or our company says, that we believe that the global electricity market is going to triple before 2050, and a lot of that new electricity is going to be used for data centers and AI and also robo-taxis and robots and so on. We have to think about where's all that energy going to come from. And just before we started this show, you and I talked about natural gas is maybe the best solution in the short term, sort of the next 5 years, but there's a limit to how much natural gas can scale. And then if we start to look at nuclear energy, of course, we have to look at how quickly could that be built out. There's already 30 countries who have signed up to sort of in one of these COP 28 or 29, they agreed that we should triple the total amount of nuclear energy in the world by 2050. So, I mean, they are already on the same path. But since nuclear energy is, like you said earlier, is only 15% of all electricity, so tripling nuclear energy, it sort of barely helps. I mean, of course, gas and nuclear can help, but some of the other energy sources are not able to triple. And one example is hydropower. That one it's really difficult to get much more out of that one. So some of these energy sources that we can scale, gas and nuclear power, would have to scale much more than tripling. And in our estimates, we're looking at, can we make 10 times more nuclear power? And that would mean, again, 10 terawatts by 2050. And I honestly think it's possible, but of course we need to change the regulations so that it becomes easier to get these reactors approved and manufactured. And one of the things that we can see if we look at the airplane industry or the car industry, you don't have to get every single airplane or car approved. You get a type approval for a certain type of airplane, and then you can make as many airplanes as you want, and you can fly them to almost any country in the world. And I think we need the same for nuclear reactors. For example, our company, we want to mass manufacture these reactors. We want to make, at least one reactor every day, and we should be able to get that type of reactor approved, and then we can sell them to maybe not all countries, but all the countries who agree to sort of a common approval practice. And then we wouldn't have to get it approved in every one of those countries. And also that approval process shouldn't take 10 years or 5 years. It should take 1 year or at most 2 years. I think that would be reasonable. But these are some of the things that we have to think about as a global society. How do we want to power the future, and how do we want to make it a safe future? Because every energy source has its drawbacks. I mean, some people are afraid of nuclear energy. I think that's there's no proof of nuclear being dangerous, but we have to accept some people are afraid of it. Some people are also afraid of flying. Other people don't like wind and solar because it takes up a lot of space in nature. Some people don't like fossil fuels because it's CO2. And I mean, you can't find any fuel source where everybody agrees this is this is perfect.
Right. So a few comments upon that. As I was just showing, there's been an executive order from President Donald Trump today that will require the Nuclear Regulatory Commission, the U.S. Regulatory body on nuclear, to decide whether to approve a nuclear reactor within 18 months. So you'd ask for 1 to 2 years. That 18-month approval process is what they have now working towards instead of the many-year approval process. And the environmental often takes 2 to 3 years. So they're saying all approvals within 18 months. There's also aspects of the executive order discussing also uranium and many other things to streamline. In terms of the overall feasibility and goal of getting consistent reactor time construction, the nuclear reactors that were built in the United States were primarily built in the late 60s and 70s, and those did have relatively consistent construction times in the 4 to 8 year time frame, which is what France was able to do when they converted and made 55 nuclear reactors in the 1980s, and what China and South Korea are able to achieve with 4 to 6 year construction times and costs in the range of about $2 billion per gigawatt is a price point achieved by China. So it's not something physically impossible to be done. The fast, consistent construction times are possible with regulations that are safe. One, the nuclear reactors, over 100, although now down to 94 in the United States, they had the one accident which did not release any nuclear material, and in 3 Mile Island, and the Chernobyl accident was a exceptionally unsafe Soviet design, which was the main one that actually caused any death on its own. But in terms of other fuel sources, you have to say compared to what? Compared to perfect, yes, not perfect. Compared to other things is something that I've written about extensively in the death per terawatt hour analysis, where you say, okay, how many deaths actually occurred for any energy source? And nuclear is down with solar and wind in 100 times safer than coal, natural gas, and oil, which we know kills millions every year with accelerated death from particulates, air pollution, and water pollution. And I've gone extensively around those dangers. And even solar is not perfectly safe because if you install solar on your roof, roofing is the 5th most dangerous profession in the world. And just because you have only a few dozen or a few hundred people falling off roofs and dying or getting injured, that is still a significant factor that just because it wasn't something that you're scared about, it's still causing death and injury. So there is progress today on getting the regulatory on nuclear cleared up. Not sure what's going to happen in Europe, but certainly France did not restrict their nuclear regulatory thing as much. And these are huge factors because the cost for building nuclear is a more upfront cost, and then takes time to then generate that. So for people who don't know finance, if I need to borrow $1 billion, then the longer it takes me to start recovering and making money from that, then the worse the economics are. Just like if I, make a big apartment block or shopping mall, I want to shorten the construction time, shorten the time before I can make money, which is actually also where Copenhagen excels, because you're making many small units and can want to factory mass produce them like planes. And 1,000 planes are made a year by Boeing, 1,000 planes are made a year by Airbus, that you could then produce these high volume. And then if that time to order, fund, and then install and start making money, that if you're going to install 100 units, you can start making money off the first units earlier. Do you want to discuss some of the economics and financing around that?
Yeah, I just want to briefly mention that we expect that a 1 gigawatt power plant, that the one you showed in the picture before, with 25 active units, will cost you roughly $2.5 billion in the 2030s. Hopefully, when we get later into the future, we can reduce that cost. But comparing that to the $20 billion for a 1 gigawatt light water reactor that we have seen some of the other projects, it's almost 10 times cheaper than some of these other offers. And I think that goes a long way. And then, like you said, we can manufacture one reactor every day, and out at the site where you want to install it, we can install 1 unit per week. So it's a completely different timelines than the classical reactors. But of course, we also have to be honest and say that our type of reactors have not been approved yet, and they are not up and running. I mean, the real proof is there when we actually start to install them, and actually start to install one every week, for example. Then people will start to believe it. And I understand that people are sort of, this is a future projections right now. But it is coming. I'm sure it's coming. And I know that there's other companies trying to achieve some of the same things. So I think we're not the only ones. There will be a number of companies trying to achieve this sometime in the 2030s. I would say one of the unique things about Copenhagen Atomics that maybe some of the other companies doesn't have is that we run our reactors on thorium, and there is 1,000 times more thorium in the world than there is uranium-235, which is most of the other nuclear reactors run on uranium-235, and that uranium-235 in most cases are even enriched 235. So you need to build out the enrichment capacity, and right now there's only 2 companies in the Western world that builds enrichment factories. That one called Urenco, another one is owned by the French government called Orano. And that Orano, for example, is actually building a new plant in the US for enrichment capacity. But I mean, that's one of the bottlenecks right now, is this enrichment, because some of these new reactor types, they also need uranium fuel enriched to a higher percentage, close to 20% enriched fuel, and none of those Western companies make that right now. There is a Russian one that makes 20% enriched, but we don't like to buy from Russia. Or there's all these problems, but I think these problems will get resolved. But the way I view it is a little bit of a bottleneck. Whereas thorium, there's so much thorium in the world, and we already mine. When we mine for other minerals, we get thorium out of the ground. And we actually already get enough thorium out of the ground today from mining other minerals that we can power the entire world with thorium without opening one extra mine. So that is a plus. But of course, again, we need to show that the reactors can be set up in 1 week, and that we can get the price down to $2.5 billion per 1 gigawatt power plant. I think we will get there in the early 2030s. And I think then we will start to see a lot of money being invested in this field, just like we've seen in the past that huge amount of money got invested in oil and gas because that was very profitable. And we've noticed that Europe is not very active. There is some investments from Europe, but it's definitely US investors and also Asian investors that are investing in this right now, and they're willing to invest billions of dollars. But of course, they want some guarantees, and I think this executive order that you just showed from Donald Trump helps. And I did hear that it was coming, and I haven't been able to read it before this podcast, so I don't know exactly the details, but I think it's a very positive step in the right direction, even if it's not perfect. I mean, it's yeah, we need many steps in the right direction.
So some other aspect of it is that you're currently making test loops. It's a picture of some of the things that you're making, which shows that this component test system for molten salt is something that you're mass producing in, like you see 9 or whatever in this picture. So that shows that you're thinking about making, many copies of these things and not just crafting one at a time. Do you want to discuss the fact that everything going towards this mass production
Yeah,
vision?
let me explain that a little bit. So clearly these test systems we have in the picture here, they are not nuclear reactors. They are test systems. But before you can put, it's a little bit the same with a new mobile phone or a new car or something. Before you can put hundreds or thousands of a new a commercial product in the market, you need to test it very carefully. And for nuclear reactors, there's very high requirements on the reliability, and that means we need to do a lot of testing. So I'm expecting that we need to run 1 million what is called pump hours. That basically means that all of these machines are pumping salt around for 1 million hours before we can release the first commercial product. And we've already started doing this a number of years ago. And by far in the whole world, we are the company with the biggest molten salt test capacity. We also sell these systems to other universities and national labs. There's a number of universities here in the US, for example, UC Berkeley and MIT, that have bought a number of these systems for testing molten salt. Right now in Copenhagen, we have the capacity to run 20 of these, but we want to increase that to more than 100 test system running. And we do that because we want to find all the problems and all the errors before we put the first commercial reactor in the market. And of course, these test systems are smaller and less expensive than building full-scale reactors. In Copenhagen, we also have 2 full-scale reactors where we are testing the same way. We're heating up the salt with electricity and pumping it around and testing thermal expansion, thermal cycling, all kinds of things that we need to test before we bring the first reactor to Switzerland and let it go critical in 2027. So, I mean, we are doing all these things to get the first approval and do all the testing that we need to do. And if I look around in the industry and look at all the other players, I don't believe that there's any company out there that has like just a handful of operating molten salt loops, or also there's no other company that have full-scale commercial reactors operating sort of prototype states before we call that subcritical, but when it's before they go critical. So we're definitely trying to pave the way forward for that. And most of the other companies are not quite there yet, but of course, like I said, there's lots of investor money right now in this field, and I do believe that there will be a number of companies and a very positive, or what is a competitive market in the 2030s between these different companies.
What are you finding in Europe? Go ahead, you want?
Yeah, there's one thing I wanted to mention that you were talking about before, that all different types of energy sources have casualties and they make pollution. And you're absolutely correct that coal-fired power plants, for example, everybody agrees that's the worst one. It creates more than 1 million deaths per year, and that's not even including any potential death from CO2. This is from air pollution and mining and construction of the power plants. If you look at nuclear energy, there's a couple of numbers I just want to mention because normally people don't know this. So we've had sort of a few accidents. There was the 3 Mile Island accident. Nobody died from that one. Then there was the Fukushima accident in Japan. Only 1 person have been confirmed to die from that one from radiation. Unfortunately, in Japan, there was 150,000 people that were evacuated, and some of those people have died from having their whole life uprooted and lost their job, lost their company or whatever. But that's sort of not from radioactivity. That's from maybe bad decision from
response.
the
Yeah,
government
yeah.
to yeah to evacuate because they shouldn't have been evacuated. But that's a whole other story. Then from the accident in Chernobyl, there was 31 people who died sort of in the first couple of I think in the first year after the accident from radiation exposure, and then later on there were some people who died from cancer, and you can always debate how many of those people afterwards were from the accident, but it's far far below the numbers we see from fossil fuels, for example. And you're absolutely right that if you look at wind and solar, there's also some casualties. A lot of those are from installing the wind and solar equipment, but also from the production, the supply chain, the mining of iron, the smelting of iron, and it's also the case in nuclear. If you look at the number of deaths per terawatt hour in nuclear, almost 60% of those deaths come from mining of uranium. And there's almost no requirements or no legislation around the safety and mining of uranium. And so it's a little bit odd that we say nuclear is unsafe, and then we have sort of lots and lots of regulations on the nuclear power plant itself. And the nuclear power plant has almost never killed anyone. And we have almost zero regulation on the uranium mining, which actually kills people. So, yeah, but that's just the world is not perfect, and we have to still operate in this environment.
Yeah, just to discuss that, I've written a few dozen or 100 articles related to energy safety comparison. So the um, Chernobyl unsafe nuclear power plant, which was just an incredibly insanely bad design. There was an insanely bad hydroelectric dam that was made with China's Mao with help from the Soviets, and that was the Bangchao Dam, which was originally basically piled up dirt and then they put some cement on it. That dam broke, and it killed about 250,000 people. It was in the I think late 70s or I think or early 80s that occurred. They had to send fighter jets and bombers to destroy the other um, sub dams related to that dam as they realized it was going to break in order to prevent millions of people from dying, right? Because that it was going to flood and kill, some major city. And so they had to were doing insanely bad stuff. So basically, insanely bad engineering can cause a lot of deaths, and that's hydroelectric. And going back over the many years, people don't realize there have been many other deaths from various dams, hydroelectric dams. There's also dams related to coal.
Mm,
Coal, you blow up a mountaintop for some things in order to scoop out the coal from the mountaintop. One, you just blew up all the animals and trees that were on top of that mountain before you scooped out the stuff. All of that material, trees that got pulverized and dirt go sliding down to the bottom of the valley, and they have a little dam there to hold back this amount of sludge. Those dams have broken, and there's, I think it was Buffalo Creek or some other dams in the United States that broke, and then you have this toxic waste of stuff that went flooding out, and it caused a little tsunami that killed a mining town, killed 100 people, stuff like that. So
mm,
people don't realize there's all this trail of death related to if I'm moving a lot of stuff, 8 billion tons of coal, and I had to move 50 billion tons of dirt and stuff to get there, that movement of a huge amount of material causes death. Moving it causes death. 40% of all freight rail is moving coal around between the power plants because I need to have like there's some coal plant a few hundred miles away from some large facility, I think in Montana, and they would then send these coal trains, hundreds long, 20 trains going in order to get the hundreds of thousands of tons of material every year. So that means constantly there's trains. They open up at the bottom, dump the bottom of their coal out as they pass over some conveyor belt system to move the stuff. But then 40% of all freight coal accidents can basically say, okay, that's coal, because I had to move 40% of my material. So that's globally in the United States, Europe, China, where the movement of freight rail is almost half movement of coal. Same thing for movement of a lot of oil. So the lack of density of these energy sources causes problems, making the pipeline, making the steel. So They're making now hundreds, heading toward the 100 square miles of solar in China, filling up Tibet and all that kind of stuff. They have 10 times the amount of steel and cement to generate the same megawatt for solar and wind versus nuclear. So then if I have to have 10 times as much steel, then all the deaths for steel and cement can, the larger portion goes to that. So yes, it's an overall systemic effect where the safety of nuclear being more contained, being more dense is better because people talk about the waste, and the waste is actually 95% by mass uranium-238. Uranium-238 can be fissioned if you stick it in the right reactor. But because of even number, I need to hit it with 100 times more energy on the neutron side. But that material, which they say, oh, what do we do with all the material so long lived? If you put that material into nuclear reactors, and they're working on reactors, that fast reactors that can then handle that process. And there's versions of molten salt that are fast reactors that can take that. You can take all of the old material and do it. I cannot pull back and recycle any of the particulates, the billions of tons of particulates that are all over the world, all the mercury in fish, that's from coal. So I can't pull that back. The nuclear, I can. I can stack it up in areas the size of a basketball court, and then I can then use it later. So we don't have to keep it around for a long time. So the safety profile is not understood. The comparison to the other energy sources is not understood, and um, um, the other aspects, that I've been discussing there about materials, how much it is, are not as understood. So.
Yeah.
So we can discuss
I
that
want
more
to
later.
mention also that that is one of the unique things about the Copenhagen Atomics thorium molten-salt reactors, that it can actually also burn spent nuclear fuel. And we are actively trying to get access to the transuranics. So transuranics is 1% of the spent nuclear fuel, and that's the part that we can use in our reactor. That is all the plutonium and all the higher actinides. So we can start our reactor on that, and then it will convert into a burner that burns thorium. It converts thorium into uranium-233, and then that's the fuel going into the future. I don't know if I can share on this. I can try. Then I can show a chart.
Okay,
Or
so
you need
just
to allow
let
me to
me,
share.
yep, I'll allow that. Go ahead.
So this here is an example of a burn up. Let me just burn up of a reactor. This is a reactor simulation over. You can see 27 years here down at the y-axis, and then up the down at the x-axis. Up the y-axis, you have the number of neutrons generated per fission event, and you can see what those neutrons are used on. The blue colors are plutonium, and all the colors above the blue colors are the actinides, the higher actinides. And then the brownish color is thorium, and this dark green is uranium-233. So basically, this gives you an idea of how this reactor starts on transuranics on day one, and then slowly it burns away that transuranics, and it converts into a reactor that runs on thorium, essentially. Of course, it takes many years, and you can see the transuranics stay in the reactor, and you probably need 100 years before it's completely disappears, or there might be tiny amounts left after 100 years. But it doesn't matter when it's inside the reactor. It's a safe way to put it. You don't need to put it deep geological storage, and it actually disappears in this way while it's creating energy. And people always say that spent nuclear fuel is it's a problem. We need to pay a lot of money to get rid of it. But Copenhagen Atomics has already put out that we're willing to pay money for this. We're willing to pay $10,000 per kilogram of this transuranics. And if you split spent nuclear fuel from classical reactors, the other part that you get is uranium. And that uranium can be used directly in candid reactors. And candid reactors actually use many more kilograms of uranium than light water reactors. So it would be great for the candid reactors to get access to a lot of low-cost fuel that they can burn through. So, there is really a way to take spent nuclear fuel and use it again. And in our type of reactors, we can generate 10 times more energy from each kilogram of fuel than the old reactors were able to generate. So we use it much more efficiently, and that's because we combine it with thorium.
Mhm.
Um,
Okay,
there's a few other things that you mentioned that I wanted to touch on.
okay.
So um, yeah, so well, no, wait, let's go over to you.
I just mentioned I have unfortunately a hard stop in about 4 minutes here. So why don't you wrap up with the points you want to make, and then we'll come back next time for a lot more to discuss. So there's so much more that we have to discuss here.
Yeah, absolutely. So I want to jump back to the data centers and the build out. My prediction right now is that the US is going to lead this, and China is going to be just behind by half a year or something. And those two countries are going to be the main ones where we will build out this new nuclear technology. And just like we've seen with the dot-com boom or some other things in the past, when suddenly a new technology becomes available to humans, I think this is what we will see in the next 10 years, that there will be a huge amount of investments, hundreds of billions of dollars invested into these companies who can provide this type of energy. And I think the data centers and the EVs and the robots and everything will can use all the energy we can create. I mean, the market can definitely use it, especially if we can build it fast enough and get the price far enough down. And for Copenhagen Atomics, we target a price of $20 per megawatt hour in the 2030s. So probably we will hit that price by 2035. And that is a price which is lower than the price of coal, what coal costs today, and of course, significantly lower than gas. But like you said in the beginning, I mean, there will probably not be enough nuclear, there will not be enough gas, there will not. So we will have to use all of them, wind and solar and hydro and nuclear and even different types of nuclear. So I think it's a very exciting news. And I think this century will be defined by how fast we can build out energy, a little bit like it was in the old century. I mean, oil and gas was definitely a big part of the history in the last century. So I think it's very exciting.
Yes, I think it's very exciting and a lot more to follow. Many developments will happen because things are moving so quickly. So look forward to having you on next time. And so we'll talk again. Thank you.
Yeah, thank you for having me. Have a great day.
Bye.